Right. Good morning, gentlemen. I hope you are doing well.
Good morning, sir.
Hang, is it you?
No, sir, I'm doing so, sir.
Very good. Okay, guys, let's continue. Okay, we were talking about unit step function yesterday, and we did a few examples related to unit step function. And also, since Laplace transform of f of t minus a times u of t minus a, right? That is equal to e to the power minus as times f of s. So actually we give this as a theorem. It was a theorem, right? Using this, we got this result. Since Laplace transform of this f of t minus a times u of t minus a equals e to the power minus as f of s. All right, then it is inverse should give us this, right? So if you just take the inverse of both sides, then inverse of this f of t minus a, or inverse of e to the power minus as times f of s is equal to this. Why? Because of this theorem, right? Okay, now sometimes you will see that in this we have what we have here. The function, right? The input here is t minus a. And also here we have t minus a. But now we will consider another case, but because most of the case, actually we are frequently confronted with the problem of finding the Laplace transform of a product of a function g and the unit step function u of t minus a, where the function g lacks the precise shifted form that f of t minus a. All right, but instead of here t minus a, how about if we have something like this, g of t times u of t minus a. Okay, how do we evaluate this Laplace transform? Of course, actually directly we can, by using the definition, we can evaluate this. So since we are going to encounter such problems frequently, so it is worth to get a formula for this so that we can use this frequently. Okay, that is alternative form of theorem 7.3.2. That is Laplace transform of g of t times u of t minus a, that is unit step function, is equal to, here we have e to the power minus a, e to the power minus as, but here we have Laplace transform of g of t plus a. Okay, so now we try to get this thing. Here, using the theorem, we know that Laplace transform of f of t minus a, or let's say g, all right, here g of t, okay, g of t, all right, g of t, and here we have u t minus a. Okay, so using the definition, what is it? It is integral from 0 to positive infinity, right? And here we have e to the power minus st times g of t times u of t minus a, right? Here we have dt. Okay, but now if I just denote this thing by this, all right, here, and also we know how to evaluate this when actually this changes from 0 to a, because of this thing is equal to 0, right? And here is equal to from a to positive infinity. Here I have e to the power minus st times g of t dt. Okay, so now instead of this t, if I just write here, let's say u is equal to t minus a. All right. So as a kind of substitution methods, I want this to start with 0. So if I label this t minus a as u, here we will have t will be equal to u plus a, right? And also from here, when t equals a, u will be equal to 0. right? Because if t equals a here, u will be equal to 0. And when t goes to positive infinity, also u goes to positive infinity, right? This is t, here just u. So making these substitutions here, then I can write, I'll just change this independent variable. What is a? Here now, a, right? So if I change this t with u, then u starts with 0 to positive infinity. Here we have e to the power minus s times what is t? From here, t equals u plus a. So here we have u plus a times. And how about this here? G, here we have g, right? And t is equal to u plus a. So here we have u plus a. And here I have d. What is t? T is u plus a. That is u plus a. We know that dt here is equal to du because a is just a constant. So here we have du, right? Okay. So what we have here, now our independent variable is u, right? And here, e to the power minus s times a, it has nothing to do with u. It's not dependent on u. So I can just take this out of the integral. So here we have e to the power minus s times a times what we have here from 0 to positive infinity, e to the power minus s times g of u plus a. Here we have d, right? Here we have u equals e to the power minus a sa or as because a is constant. I think I better write a first. As also here minus as. How about this integral? Here we have e to the power minus su, that is su, right? And here we have g u plus a du. So this is our function, right? If you remember, whatever we have here in the function f of t, here we have capital F of s, right? So this thing is, what is it? It's just Laplace transform of g. What is u plus a? U plus a is t. That's all right. Here we have u plus. All right, guys, I think I need to add one more step so it will be more clear for you. Because we got used to write this independent variable using t, e to the power minus as times. Here we have our variables is u. It is u. As you know, actually, it's like a function, right? Here we have y equals f of x, right? And here we are just saying this x. Instead of this independent variable, I can choose anything. Also for integral, here we have f of z dz, f of x dx, f of y dy, f of s ds. Doesn't matter what actually letter you are using for this independent variable here, right? And that's why here u, now we got used to using only t. So instead of u, I can write only t. I can use actually t. Here we have e to the power minus st times g of t plus a dt. These two integrals are exactly the same. It's all about just labeling. So now this is equal to e to the power minus as times, what is this thing? It is just Laplace transform of, that is Laplace transform of g of t plus a. Okay, that is what we are trying to prove here. That means that if Laplace transform of g of t u t minus a equals e to the power minus as, because of this one, now it's coming inside, right? It's plus, so here we have g of t plus a. I don't know about the nature of this function here. That's why I can't say anything. If you know that now, I can evaluate this. Okay? All right, let's do one example regarding this. So here, evaluate cosine of t times u of t minus pi, right? That is our unit function, right? What is a here? If you just identify from our formula, a is equal to pi, right? Then Laplace transform of cosine of t times u t minus pi, right? That's equal to e to the power minus as. What is a is equal to pi s times, right? Laplace transform of g. That our g function, this one is our g function, right? G of t. Now what we have here, g of t plus a. So that is cosine of t plus a. What is a? It is pi, right? Now actually we just transform this thing into simpler form. Now instead of the product of two functions here, I have a single function here. It is much easier to evaluate the Laplace transform a single function, right? As you know here, if you have product, now we will see another case soon. Okay, every time if you use a definition, you have to go through a long integral calculation. All we are trying to do here is when we just encounter such problems, so we want to reach the result in the shortest way possible. All right. All right, continue. Here, now if you evaluate this, here we have e to the power minus pi s times, and we now have to evaluate the integral of this function, right? It is cosine of t plus pi, right? So if I have here, let's say capital T, what I have here? Here we will have integral. Okay. T plus pi. Okay. Equals, I'm just going to use cosine of t plus pi, right? That means cosine of pi plus t. What is this? By just using simple property of cosine. We know that for cosine, here it is plus, minus, minus, plus. So here, this is our pi. Pi plus t is something, right? So here we know that the function does not change at this point. So that's equal to minus cosine of t, right? So now because of this one, I can take this minus out. So that's equal to minus times Laplace transform of cosine of t, which is equal to minus e to the power minus pi s times, we know how to evaluate it is Laplace. That's equal to what we have here, s over s squared plus 1 squared. It's just 1. Because here the coefficient of t is equal to 1. All right. Let's say another example. 9, 10. Before I continue, we need to have, I need to add two slides here. All right, solve y prime plus y equals f of t with the initial condition y of 0 is equal to 0, where f of t is a piecewise defined function. When t changes from 0 to pi, the value of the function is 0. And when t is greater than or equal to pi is equal to 3 times cosine of t. Okay. And since, as you know, this is all about using unit step function, right? And that is piecewise defined function. So first, we will express this f as a single function here. And you know that with the help of unit step function, we can do that, right? From 0 to pi, it's equal to 0. And after that, it's equal to 3 times cosine of t. How can we do that? That is f of t, right? If you remember, that's equal to this 3 times cosine of t. I can just write here 1 minus unit function t minus pi. We have seen this before, right? Now, as see here, if t changes from 0 to pi until pi, this function is equal to 0. No. If it is 0, it should not be like this. Okay, that is not like this. I need to write like this. Here we have until it is 0. So here we have about like this, u t minus pi times 3 times cosine of t. It is like this, right? Because 3 times cosine of t until pi is equal to 0. After that, 1. Okay, it's like this. Good. So it's just like 3 times cosine of t times unit function of t minus pi. Good. Now I have expressed piecewise defined function as a single function. As you see here, if t changes from 0 to pi, 0 to pi, this thing is equal to 0, 0 times that thing is equal to 0. So our function is until pi, it is off, it is 0. And after, once actually t starts assuming values starting from pi and greater values, right, is equal to 1. So our function is equal to this thing, right? Very good. And also initial condition at 0, that's equal to 5. And also we have to keep this in mind. Okay. So, all right, we will continue then. So now I can rewrite this equation. Let me just use a bit darker color. So now I can write our equation y prime plus y is equal to, what is f of t? That is 3 times cosine of t times u of t minus pi. Okay. And if you just use Laplace transform, here we have Laplace transform of y prime plus Laplace transform of y is equal to Laplace transform of 3 times cosine of t times u t minus pi. Right? Good. We know how to evaluate this. This thing is equal to the first order, just s times, here we have capital Y of s, minus what we have here, minus y of 0. That is given here. Plus, how about this thing? That is capital Y of S, right? And on the right-hand side, here we have 3 times Laplace transform of cosine of t and u t minus pi. And if you remember, we have just done this example, right? In the previous slide, let's see here. Where is it? Here. Cosine of t, u of t minus pi. That is equal to this thing. That is minus e to the power minus pi s, s squared plus 1. So I can write the thing here. And by substituting these things, what I have here, this y of s, okay. So y of s is a common factor. So here we have s plus 1 times y of s, and y of 0 here is equal to 5. Let me just take this to the right-hand side. It is 5 plus 3 times. What is the Laplace transform of this thing? If you remember, we have minus in front. So I will put minus here. Minus, here we have e to the power minus pi s, right? Times, and just cosine of t is Laplace transform, that's equal to s over s squared plus 1. Okay, that is what we have on the right hand side. All right, so now 1, 5 minus 3. Okay. Now if I just divide both sides by this s plus 1, now I get here y, capital Y of s is equal to what we have here. 5 over s plus 1, right? Minus, there we have 3 times e to the power minus ps times, here we have s over s squared plus 1. So here we have s plus 1 times s squared plus 1, because I have divided both sides by this. Both sides by this, right? Okay, now this e to the power ps, let me just write this 3. Okay, let's just keep it here. I can write it here. Here we have 3s, 3s plus 1, s squared plus 1, right? And also we have to decompose this fraction, algebraic fraction. Because here I have something like this, 3s over s plus 1. And here we have s squared plus 1. That is, how do we decompose this? That's equal to a over s plus 1 plus b s plus c over s squared plus 1. Because here we have quadratic expression and it's not factorizable. We cannot factorize it, right? And you can just bring into the common denominator, and after that we can determine this a and s. And what we have here? Here we have y of s will be equal to 5 over s plus 1. Here we have 5 over s plus 1. And this thing is equal to minus 3 over 2. 3 over 2 minus 1 over s plus 1. And here we have e to the power minus pi s, because this thing belongs to every term inside the parentheses, plus, and after that we have s squared, so 1 over s squared plus 1 e to the power minus ps, plus, because also I have to separate this and also take this b out, what we have here, s over s squared plus 1 e to the power minus ps. Okay. All right. And this thing, you know how to do that. After that, we have this thing. Okay, here we have 5 over s plus 1. We know how to find it is inverse. And also, we know how to find inverse, because here we have e to the power minus pi s. It just gives us that unit function. And also s squared plus 1. If you remember, that is, what is it? Sine function here. And how about this one? That is cosine function. But these two things are multiplied by unit function. And this one, because of e to the power minus ps, pi s, that is unit function of t minus pi, right? So now we can find it is inverse from here, Laplace inverse of, for example, this thing. Okay, what is this? It is 1 over s plus 1 e to the power minus ps. That is equal to e to the power minus t minus pi. And here we have unit function t minus pi, right? Because if you remember, here we have, what is it? F of s, right? E to the power minus pi s. That's equal to f of t minus pi, because this function's, what is it? Inverse of this function is e to the power t. But instead of t, we need to put here t minus pi, right? In similar way, how about inverse Laplace of the second thing? 1 over s squared plus 1 e to the power minus ps, right? And this thing is, we know that it's just, what is it? Sine of t, right? But here, because of this one, we need to write here sine of t. But if you remember, here we need to write here f of t minus a. Our a is pi. So here we have t minus pi times, here we have unit function u, that is t minus pi. All right. In a similar way, I can find the last one, this thing, that is inverse Laplace of s over s squared plus 1 times e to the power minus pi s, right? And also you are familiar with this. What is it? It's just cosine of t. That is, here we have cosine of, because of this thing, here we have t minus pi times unit function of t minus pi. Okay. So next, if I just combine all of the things, right? Instead of this thing, I should substitute this thing. Instead of this, we have here. Instead of this, we have here. And we know how to evaluate this. It's just 5 times e to the power minus t, right? And write them together. It gives us the solution of the given equation. So now we can write here, then what is the solution of the given equation? That is inverse Laplace of that y, right? Y of s. And we have just found this y of s here. This y of s is this thing, right? And also this inverses we have already evaluated here. The first one is minus 3 over 2 sine. And next one is also here we have u, okay, e to the power, sine and cosine. Okay. Then what we have here, the first thing is 5 times e to the power minus t. That is our first term, right? The second one is here we have minus 3 over 2. So actually I can just keep this outside or multiply each by this minus 3 over 2 times. So the first thing is this thing, right? So that is e to the power minus t minus pi times unit function t minus pi, right? And next thing is, it is sine. Here we have minus 3 over 2. All right, let me just search. I need more space. Minus 3 over 2 times sine of t minus pi times u of t minus pi, right? And the last one is cosine minus 3 over 2 times cosine of t minus pi. And here we have u t minus pi. Okay, now we can simplify this maybe. All right, so as you see here, except this term, right? Here we have unit step function, unit step function, unit step function. And we know that this unit step function, it is equal to 0 if our this input value, this t, is less than pi, right? So again, I can just write this as a piecewise defined function. And this thing actually, what is it? That is equal to, that's equal to just this function, 5 times e to the power, okay, is equal to 5 times e to the power minus t. Here we have if t is between 0 and the pi. Okay, and that's equal to this thing, the whole thing here, that's equal to, let's say, let me just write the whole thing here. Okay, if t is greater than or equal to pi. All right, that is the solution of the given differential equation. All right, guys, we have one more example. This time I'm not going to write one by one. We'll just have a look to get some information. This application in construction material, okay? And I will finish this session. In section 5.2, we saw that the static deflection, y of x of a uniform beam of length L, carrying load W of x per unit length is found from the linear fourth order differential equation. Okay, that is how it is modeled. And also yesterday, a few students, they presented about this. And most of you are civil engineering students. You should even know better than me about this kind of beam, right? Here we have a beam, and the load which is placed over this, on this, is also subject to change. It is a kind of function. It's not constant, right? Maybe here we have more load, here we have less and less and less, okay? So this model is given by this. You know, what are these things, right? A is Young's modulus of elasticity, and I is a moment of inertia of a cross section of the beam. Anyway, So here we are not going to study about the engineering part. Here we are going to start the mathematics part. So as an engineer, let's say you are dealing with this kind of problem and you face such a problem and you already modeled this. Now you have to solve this. To solve this question, now mathematics comes into the play, right? So they will come and solve this problem. So that is totally differential equation. Here this E and I, here we are assuming that these are constant, right? This W is a function of X. So here we are looking for Y. What is the value of Y, right? The static deflection of a uniform at different points. How about here and here at this point? What is it? Okay, so we have to study this. To do this, we need to solve this differential equation. It is the fourth order differential equation. Now let's consider this example. It says that a beam of length L is embedded at both ends, right? It is fixed maybe to the walls, as shown in figure 7.3.8. So we are talking about this figure. This is a wall, maybe this is another wall. It is embedded here and also here, right? It is not movable at these points. So what is changing here? Because of the load here, right? The shape of the beam is changing here. And how is it changing? It is how much we are trying to find this out. So also it's given that find the deflection of the beam when the load is given by, the load is given by this, okay, when X is between 0 and L over 2, and after that it is just constant, it is 0, no load is put, right? Here, as you see here, we have some loads until this L over 2, but here we have nothing. Okay, if it is so, how do we solve this? Again, from here, this is a piecewise defined function, right? And we know that by the help of unit step function, I can express this as a single function using unit step function. So in the first step, and also we have to consider this boundary conditions, right? Deflection at endpoints, right? As because at this point at 0, it is just embedded to the wall, and also here the change is nothing is changing here. It is 0. Also the other end is equal to 0. Okay. So first step, we have to express this W using this unit function. So that piecewise defined function can be expressed in this way. As you see here, until if X is less than L over 2, this thing is equal to 0, function equals this, right? If X is greater than L over 2, until L, right, this thing is equal to 1, so this minus this is equal to 0. Okay, so now here, if we just do some simplification here, W sub 0 is a common factor, 2 over L is a common factor, 2 take this to the outside, and it just becomes, it takes this form, right? Now, next thing is, I have to take Laplace transform of both sides of the equation. What equation? That given equation. We are talking about this equation, right? E I, right? D to the power of 4 y. Here we have d x to the power of 4 is equal to w of x, right? And w of x, that is our function here, right? And if you just take the Laplace transform of both sides, this thing is constant. I just keep it here. Right here we have 4, that is s to the power of 4, s to the power of 3, and 2, and 1, and 0. So here we have capital Y of s, that is the Laplace transform of y. Maybe it should be, yes, it is y. And y sub 0 is equal to 0, y prime of 0 is equal to 0, y double prime of 0, we don't know, but we know that it's a constant number. Y triple of 0, also we don't know, it is just a constant. Actually, instead of this, soon I am going to use some kind of constant, maybe c sub 1 and c sub 2, because we are evaluating the second order derivative of this function at 0. That's a constant number, right? And on the right hand side, we know how to evaluate this thing, right? It's just a constant number. So it is Laplace transform is 1 over s times L over 2. And how about this x? That is 1 over s squared. And here we have the unit function that's equal to 1 over s squared e to the power minus L over 2s. So this L over 2 is, this thing is in the formula, what is it? It is our a. And also this thing is our a. X minus a, u x minus a. That's equal to e to the power as, right? And here we have Laplace transform of this thing. So, and after that, if you just simplify this, these things are gone, is equal to 0. That's also equal to 0, right? Here we have EI, divide both sides by this constant, that's why it is here, right? S to the power of 4 YS, and here we have S times Y double prime of 0, and Y triple prime of 0 here, right? And on the right-hand side, there's some simplification, or just bring this down here. That's all. You're not doing anything big here. So now what is the next step? You know that we have to isolate this capital Y of S, right? Here, if I denote this Y double prime by C sub 1, Y triple prime of 0 by C sub 2, and take everything to the right-hand side and leave Y of X, because just an algebraic equation. Now we will get this thing. And also you're familiar with this. When you just do this in the paper, I know that it takes a lot of time. If you try to solve this question, you have to spend about maybe 30, 35 minutes. But here I'm showing you to get some idea, so that when you have such a problem, we know that when you model this, we have differential equation. To solve this differential equation, you have to use these techniques, these methods, right? You need to have some idea. If you want to go deep in this, you have to just sit and do this in the paper yourself. Okay, so now what is it? It is what just Laplace transform of this y, right? To get this y of x, we need to evaluate inverse Laplace of this function, right? And all of these functions, 1 over s cubed, we know how to evaluate this. 1 over s4, just we are going to use this formula, right? Laplace transform of t to the power n is equal to what? That's equal to n factorial over s to the power n plus 1, right? So I say here's just a constant number. I can just multiply and divide by this thing. I can have this thing in the numerator. And also this is the power of s cubed here, n is equal to 2, s to the power 4, n equals 3 here, s to the power 5, s to the power 6, s to the power 6. Only here we will have unit function, right? So if we evaluate this, we will have, write them separately, and the Laplace transform of the first term, the second term, the third term, fourth and fifth term. Okay, when you evaluate this, we will get this solution. So this y of x, what is it? The deflection is equal to this thing. Okay, so now we can identify this c sub 1 and c sub 2. How can we do that? So applying these conditions, y of L is equal to 0, y prime of L equals 0. Here, if you substitute L for x, I will have equation in C1 and C2. These are the unknowns, right? These things are unknowns. And after that also, y prime, differentiate this thing and substitute L for x, right? I can get y prime of L. So we will have two linear equations in C1 and C2. That is our first equation. That C1 is unknown, C2 is unknown. I know L, right? I know everything here. Also the second equation. And you learn how to solve this kind of equation, linear algebra. Just here, what we have here, we have something like this. A sub 1 x plus b sub 1 y is equal to c sub 1, right? And also solve them together, we get the value of C1 and C2. We will get the solution of the given differential equation. Okay. Thank you very much. Have a break. After 10 minutes, we will continue and have our second session. See you soon.